In this question, a ship is traveling with a constant velocity. At time t is equal to 0, the ship's position vector is given. Find the position vector of the ship after t hours. So we use the logic of vector equation of a straight line. So imagine this red line is the path taken by the ship. A is that point 300, 100, which is the original position vector of the ship. We are supposed to find the position vector after t hours. So in this case, let's say this R point actually should be S. So OS is the position vector of the ship after t hours. Vector equation of a straight line is given by this equation. R is equal to A plus T times B, where A stands for the original position vector, which is 300 and 100. T is the time, B is the velocity vector, which in this case is minus 12 and 15. So let's put all the values in. We'll get R vector, which is OS vector is equals to A vector, which is 300 and 100 in the column notation, plus T times the velocity vector is minus 12 and 15. And that is the answer for part A. In part B, it said that a lighthouse is located at a point 129, 283. We have to find the time when the ship is closest to the lighthouse. So in this particular diagram, imagine P is that point where the lighthouse is located. So let's write down the coordinates of point P, 129, 283. After a certain amount of time T, the ship reaches the point Q. Now, Q is that point when the ship is closest to this lighthouse. So we are supposed to find the value of that time. Since the ship, let's say the ship is at Q, the ship is closest to the lighthouse after some time T. Now, when that happens, the distance PQ. So if I connect the ship with the lighthouse, that distance PQ should be perpendicular to the line itself. Now, since the ship is closest to the lighthouse, PQ vector needs to be perpendicular to the path of the ship. Now, in this case, you can see that B vector is the vector which is parallel to the line. So that means PQ vector is actually perpendicular to B vector. B vector in this case is the velocity vector, minus 12 and 15. Now, since we have two vectors which are perpendicular, we can make use of the fact that PQ dot B needs to be equal to 0. So let's revise the concept. Whenever two vectors are perpendicular to each other, their dot product is always 0. B vector is already, we have that vector minus 12 and 15. Let's write that down, minus 12 and 15. But we need to identify the PQ vector. So to find PQ vector, we'll do Q minus P. Now, Q is the position of the ship on that particular line. For that, we can take these coordinates, which we had found in the first part. So OS vector we had found out. If we simplify this to get the X and Y coordinates individually, for the X coordinate, we'll write 300 plus T into minus 12. Let's write it down. And for the Y coordinate, we'll write 100 plus T into 15. 100 plus 15T. Let us consider these as the coordinates of point Q. Hence, we write down Q vector as 300 minus 12T, 100 plus 15T minus P vector. P vector, the coordinates of P, which is the lighthouse, were given in the question 129 and 283. So let's write that down, 129 and 283. This is our PQ vector. Let's simplify this to get the actual simplified expression for PQ vector. So we'll get 300 minus 129. If we simplify this, we'll get 171. 171 minus 12T is the X coordinate. For the Y coordinate, we'll do 100 minus 283, which is minus 183 plus 15T. So that's the PQ vector. Now we are supposed to take the dot product of PQ with B vector, which is minus 12, 15 equals to 0. Now let's simplify this dot product to get the value of time. And whenever we take the dot product, we multiply the X components together, we multiply the Y components together, and then we add it. So 171 minus 12T will be multiplied with minus 12. the y coordinate minus 183 plus 15t will get multiplied by 15, and we add this. Now the dot product is equal to 0. If we simplify this entire expression, we will get time t is equal to 13. And that is the answer for part B. Part B was find the value of time when the ship is closest to the lighthouse. So after 13 hours, the ship will be closest to the lighthouse. In part C, it's given that an alarm will sound if the ship travels within 20 kilometers of the lighthouse. We are supposed to find whether the alarm will sound or not. Basically, we have to find out is the ship close enough. In this particular diagram, the closest the ship can get is PQ. So if the distance PQ is within 20 kilometers, then the alarm will sound. So basically, we have to find the length PQ. And how do we do that? The vector PQ we already had found out, which is this 171 minus 12t as the x coordinate and minus 183 plus 15t as the y coordinate. We got the value of time as 13 hours. So let's put t is equal to 13 in these expressions. If we put t is equal to 13 in the x coordinate, we'll get 171 minus 12 into 13, which when we simplify will be 15. So PQ vector in that case, let's write that at t is equal to 13. The PQ vector will be 15 in the x coordinate. And if we take t is equal to 13 and put that in the y coordinate, we'll get the y coordinate as 12. Now, to identify the length PQ, we will find the magnitude or the modulus of PQ vector. So we use the Pythagoras theorem, square root of 15 square plus 12 square. And if we simplify this, we will get the answer as 19.2 approximately. So 19.2 kilometers. Now, going back to the question, we have identified PQ, the length PQ. So the distance, the closest distance of the ship from the lighthouse is 19.2 kilometers. In the question, it was given that the alarm will sound if the ship travels anywhere within 20 kilometers of the lighthouse. Now, the ship is actually at a distance which is less than 20 kilometers. Hence, the alarm will sound. So the answer for part C is yes, the alarm will sound. Question, we have to find the expression for position vector of the ship. So let us recall the basic expression. If an object has an initial position vector of A and moves with a constant velocity B, the position vector is given by this expression A plus TB, where A stands for the initial position vector and B stands for the velocity vector. So in this question, the A vector, which is the initial position vector, is 1, 4. And you can see the diagram on the left where the harbor is at the origin and the ship is at 1, 4. So by definition, if I connect the harbor origin with the ship, this HS will be the position vector initially. That is A vector. So let's write down A vector can be written as 1I plus 4J, or in the column notation, we can write like 1, 4. The velocity vector they have given already. So the velocity vector is 1.2 minus zero point 0.6. This is the B which we require for this expression. Hence, putting both the values, we will write down the vector R as 1, 4, which is the initial position vector, plus T times the velocity vector, which is 1.2 minus zero point 0.6. And that's the answer for part A. Moving to part B. Find the time at which the bearing of the ship from the harbor is 45 degrees. So let us understand the concept of bearing when the angle is 45 degrees. So have a look. If the bearing is 45 degrees, that means the angle with the north is 45 degrees. Here, consider point B as the north. Whenever the angle is 45 degrees, so consider this right angle triangle, tan 45 will be opposite upon adjacent. So BC upon AB. Tan 45 is 1, and that's why we get BC and AB are equal. We say the x component of the displacement AC is equal to the y component of AC. In part B, we are given that the angle required is 45 degrees. So we have to use this concept, x component and y component are equal. In the part A, we had found out the vector equation. So individually, let us identify the x coordinate as well as the y coordinate. X coordinate will be 1 plus t into 1.2 and y coordinate will be 4 plus t into negative 0.6. So let's write that down. X will be 1 plus 1.2 into t and the y component is 4 minus 0.6 t. If the angle is 45 degrees, which is in this particular case, so we will equate the x and y components. So let's do that. The x component, let's equate that with the y component. If we simplify this expression, we'll get 1.8t equals to 3. This implies t will be 3 upon 1.8. Let's simplify this. So we'll get 10 upon 6 or 5 by 3. So 5 by 3 is the time after which the bearing of the ship is 45 degrees. Now, the question was to find the time at which the bearing of the ship is 45 degrees. We already have found the t, but initially observe in the question they have given, the starting point was 1 p.m. So we'll have to add the 5 by 3, which we have gotten, to 1 p.m. And let's do that. So the time, final time which we require is 1 p.m. plus the 5 by 3. Now, 5 by 3, if you simplify, is actually 1.66 hours. Let's convert that into minutes as well. So 1.66 we can write as 1 plus 0.66. So 1 hour and 0.66 hours. So let's convert 0.66 hours into minutes. So we multiply 0.66 only with 60. That will give us the answer in minutes, which comes out as 40. So 5 by 3 incidentally is 1 hour plus 40 minutes. Now we need to add this much time to the original time of 1 p.m. So 1 p.m. plus 1 hour is 2 p.m. and we add another 40 minutes to it. So the final time will be 2 p.m. 40 minutes, which is basically 2:40 p.m. And that's the answer for part B.